acids, bases, and indicators. Now, certain foods such as oranges and lemons have a sour taste when eaten, and these foods contain acids. All acids have sour tastes. Other things have bitter taste, and such include antacid tablets, wood ash solution, and baking powder, and these contain bases. Bases have bitter tastes when ingested. The use of tests to distinguish acids and bases is not a reliable method. We have other methods to distinguish between them. Simple acid-base indicators. When flower petals are crushed and an organic solvent added, a deep solution is formed. This solution gives the same color when added to acidic solutions like hydrochloric acid, sulfuric acid, lemon and orange juices. It will then give the same color in basic solutions like sodium hydroxide, potassium hydroxide, baking powder, and wood ash solution. This color is, however, different from that in acid. The extract will, however, have no effect on solutions like water, salt solution, and sugar solutions. However, the colors obtained above keep changing with time, giving inconsistent results, and thus the flower petal solution should be used when fresh. In labs, we use commercial indicators. Commercial indicators. There are three commonly used commercial indicators in chemistry labs: the litmus solution, phenolphthalein, and methyl orange. The litmus solution is purple in color. In acid, it turns red. In base, it turns blue and maintains its purple color in neutral solutions. Phenolphthalein is colorless in acid, pink in base, and colorless in neutral solutions. Methyl orange is pink in acid, yellow in base, and orange in neutral solutions. Other acidic substances include nitric acid, carbon 4 oxide solution, sulfur 4 oxide solution, and ammonium sulfate. Basic solutions include soap solution, baking powder, toothpaste, ammonia solution, calcium hydroxide, and magnesium oxide, amongst others. Water and sodium chloride are neutral solutions. The pH scale and universal indicator. Whereas we can say that a certain solution is an acid or a base, the strength of acids and bases differ in different solutions. The indicators above did not tell us about the strength of the acid or bases. To know this, we use a universal indicator. Before we look at this indicator, let's see what a pH scale is. A pH scale has values ranging from 0 to 14. The value from 0 to just below 7 represent acidic solutions. Values from just above 7 to 14 indicate a basic solution. 7 represent a neutral solution. The pH scale is shown on your screen. Now, as you go from 7 to 0, the strength of an acid increases. A pH between 0 to 4 is that of a strong acid like hydrochloric acid and sulfuric acid. A pH of between 4 to just below 7 indicate weak acids like ethanoic acid and acetic acid. As you go from 7 to 14, the strength of bases increase. From just above 7 to 10, the values indicate weak bases. From 10 to 14, it indicates strong bases like wood ash and sodium hydroxide. Universal indicator. A universal indicator is a mixture of several indicators that exhibit a range of colors in acids and bases depending on their strength. On your screen is a universal indicator. You can see the range of colors from strong acids to strong bases. let us reactions of acids, and we start with acids and metals. When dilute acids such as hydrochloric acid react with metals such as zinc, magnesium, and iron, bubbles of a colorless gas are formed, that is, an effervescence occurs. The colorless gas is hydrogen. The other product that is usually left in the solution is the salt of that acid. Take a look at this. This is the reaction between zinc and hydrochloric acid. Great. Now the reaction can be represented by the following equation, that is zinc reacting with hydrochloric acid to give zinc chloride and hydrogen gas. If we use sulfuric acid, we shall sulfate and hydrogen. The pattern is the same for all metals, though the rate of reaction may differ. Magnesium and aluminum react more vigorously with acids than zinc, and the reactions can be represented by the following equations on your screen. Now from this, an acid can thus be said to be a compound that reacts with metals to form a salt and hydrogen. That is, acid plus metal is equal to salt and hydrogen. Very reactive metals like potassium, sodium, and calcium will react violently with acids to produce salt and hydrogen. However, the reaction between calcium and sulfuric acid proceeds, slows down, and eventually stops. Now the salt that is formed, that is calcium sulfate, is insoluble. It forms a coat on the unreacted calcium, forcing the reaction to stop due to inability of the acid to access the metal. Same thing happens when lead reacts with either sulfuric or hydrochloric acids. The salts lead to chloride and lead to sulfate are insoluble, and therefore they will form a coat on the unreacted metal, making it hard for the acid to access, and therefore the reaction will stop. On its part, copper doesn't react with dilute acids at all. The salts formed by acids include chlorides for hydrochloric acid, sulfates for sulfuric acid, nitrates for nitric acid, carbonic acid forms carbonates, phosphoric acid forms phosphates. The next reaction is that of acids and carbonates or hydrogen carbonates. When acids react with carbonates or hydrogen carbonates, effervescence occurs. The solid is used up and a colorless gas is produced. If the gas is bubbled through a solution of calcium hydroxide, that is lime water, a white precipitate is formed. The gas is carbon 4 oxide, and this is the confirmatory test for carbon 4 oxide. Let's see the reaction between hydrochloric acid and sodium carbonate. So there I have the sodium carbonate powder, and when I add acid, you can see the bubbles are forming. There is effervescence. Actually, a foam is formed, meaning a lot of reaction is taking place and a lot of gas is being produced. And as more and more acid is added, you will see more and more effervescence occurs until all the carbonate has been consumed. Now the reaction can be represented by the following equation: sodium carbonate plus hydrochloric acid to give sodium chloride plus carbon 4 oxide plus water. Now, other carbonates that will react with different acids are indicated by the equations on your screen. An acid reacts with a carbonate to form salt, water, and carbon 4 oxide. Equally, an acid will react with hydrogen carbonate to form salt, water, and carbon 4 oxide. Now the reaction between calcium carbonate and sulfuric acid will proceed and then stop due to formation of an insoluble coat by calcium sulfate. Next is acids and bases. Now the most common base in the laboratory is sodium hydroxide. When acids react with a base, basically they are neutralizing each other. The end product of such a reaction is a neutral one. The reaction is called a neutralization reaction. Now, to be able to know when the reaction is complete, we use an indicator. For example, in the reaction between hydrochloric acid and sodium hydroxide, when a few drops of phenolphthalein indicator are added to the sodium hydroxide solution, the solution will turn pink. Remember, we said phenolphthalein is pink in basic solutions. Now, dilute hydrochloric acid is added dropwise until the solution becomes colorless. Now, again, remember phenolphthalein is colorless in neutral solutions, and this is called the endpoint. The procedure is very common in chemistry practicals. Now, let's look at the demonstration of that briefly. So we have sodium hydroxide. I add to water to make the solution basic. Now I then add phenolphthalein, so you find the solution becomes pink. Now here I have acid. So if I put acid here, you will realize the pink color disappears, and that means I have neutralized the base. Now dilute acids react with bases in a neutralization reaction to form a salt and water according to this equation. For example, sodium hydroxide, the base, reacting with hydrochloric acid, it forms sodium chloride plus water. Sodium chloride is the salt. Now others would include calcium hydroxide reacting with hydrochloric acid. Copper 2 oxide is an insoluble base reacting with sulfuric acid. Lead 2 oxide is also an insoluble base reacting with nitric acid to form lead 2 nitrate and water. A base is a substance that reacts with an acid to form salt and water. Metal oxides, metal hydroxides, and ammonia solutions are bases. Acids and the environment. When gases such as carbon 4 oxide and sulfur 4 oxide are emitted, they rise into the atmosphere and combine with rain to form what we call acid rain. Now the effect of this acid rain are seen in the corrosion of iron sheets, destruction of infrastructure, metal surfaces, and also plantations. Uses of acids. Carbonic acid is used in aerated drinks to enhance taste. Hydrochloric acid is used in cleaning of metal surfaces. Sulfuric acid is used in car batteries, manufacture of fertilizers, paints, and detergents. Nitric acid is used in the manufacture of dyes, paints, explosives, and fertilizers. Ethanoic acid and citric acid are used as flavors in foods. Bases, uses of bases. Magnesium oxide or hydroxide is used as an anti-acid tablet. Calcium hydroxide or calcium oxide are used in neutralizing soil acidity. They are also used in cement or concrete making and also in toothpaste. Ammonia solution is used as a degreasing agent, manufacture of fertilizers, and manufacture of nitric acid. Sodium hydroxide is used in the manufacture of soaps and also as a degreasing agent.
What are you looking for in a college? Many students discover that when they attend a large university, they become just another face in the crowd. Well, not at SAGU. Here, there is one professor to every 19 students. That means instead of being a face in a crowd, you know and interact with your professors personally. You'll be joining more than 2,000 students from 46 states and 35 countries for a college experience like no other. Because at the center of everything we value are our commitments to Bible-based education and academic excellence. Here at SAGU, we offer more than 60 degrees, a full selection of sports, clubs and organizations, and international travel to make your life as a SAGU Lion a memorable and empowering experience. Our average annual cost is half of the national average for other private schools, and we award $28 million annually in financial aid, with 92% of students receiving some form of financial assistance. Now, you might be wondering, where exactly is SAGU? Well, you know where Dallas, Texas is, right? SAGU is in Waxahachie, just south of Dallas and Fort Worth, close enough to benefit from the restaurants, pro sports, activities, churches, and jobs of a booming metroplex. So, if you haven't given SAGU a close look, perhaps it's time.